In a monolithic application, failure is usually binary. A bug triggers an unhandled exception, and the process crashes with a clear stack trace. But in a distributed microservices architecture, the network introduces a quieter, more insidious failure mode: latency. Consider a standard architectural baseline. A user opens a client portal, which calls a recommendation service. To figure out what that specific subscriber is allowed to watch, the recommendation service must synchronously fetch user data from a downstream entitlement service. Trouble begins when the entitlement service database experiences unexpected load. Its response time jumps from a crisp 50 milliseconds to a sluggish 5 seconds. Think of this like a busy restaurant with a single, slow dishwasher. Dirty plates pile up. The line cooks, waiting for clean pans, stop cooking. The waiters, waiting for food, stop serving. Eventually, the hostess stops seating guests. A single bottleneck in the back of the house quietly brings the entire restaurant floor to a halt. Translated to our technical reality, those trapped cooks and waiters are inbound HTTP worker threads. Because the downstream entitlement service is taking 5 seconds to reply, the threads inside the recommendation service are forced to block, sitting idle while they wait for network I/O. This is a state known as thread pool starvation. As concurrent user requests keep pouring in, the upstream server rapidly depletes its operating system socket descriptors and memory buffers, just trying to maintain this growing army of blocked, waiting threads. The consequences hit the front door almost immediately. The API gateway starts returning 504 gateway timeouts, the recommendation service is entirely locked up, and the outage propagates straight to the end user. A multi-second delay in one unglamorous downstream service will systematically destroy an entire cloud platform if the components lack strict mechanical isolation boundaries. To stop a cascading meltdown, the system requires a rigid structural defense. It has to learn how to explicitly say no, rather than waiting helplessly for a response that might never arrive. This pipeline topology diagram outlines the request path. We place the protection here: a unified, zero-allocation poly V8 resilience pipeline sitting directly on the outbound HTTP client. It intercepts every request before it leaves the service. The first line of defense is a strict time limit. Traditional 5-second timeouts are fatal under high concurrency because 5 seconds is more than enough time to exhaust a thread pool. Enforcing an aggressive hard timeout, like 2.0 seconds, salvages those threads before the OS runs out of resources. But timeouts alone don't solve widespread degradation. When widespread downstream failure is detected, the ultimate defense mechanism takes over: the circuit breaker state machine. Looking at this state machine, normal operation happens in the closed state while silently calculating failure ratios. Once that 50% threshold is breached, the breaker trips open. Every subsequent call is intercepted instantly. 0 network calls are attempted. The mechanical advantage of this fast fail is immense. By returning an immediate HTTP 503, the upstream worker thread is instantly freed to handle other requests. The risk of thread pool starvation is completely eliminated. After a 15-second cooldown window, the breaker enters a half-open state, letting exactly one trial request through as a downstream probe. If that single probe succeeds, the circuit closes again. Normal traffic is restored automatically, requiring 0 manual intervention from operations. Circuit breakers function as a deliberate amputation mechanism, severing a failing downstream dependency before the outage spreads to the core platform. Circuit breakers reliably protect against downstream failures, but a secondary, hidden threat often takes down systems at peak load, relying on reactive caching architectures. The traditional cache-aside pattern works by checking the cache first. If there's a miss, the application queries the database, computes the result, and writes it back to the cache for the next user. This creates a dangerous vulnerability known as the thundering herd. If a popular cache key expires at peak traffic, thousands of concurrent read requests bypass the cache and stampede the primary database, crushing it instantly. Netflix solved this at scale using the EVCache pattern, which inverts the standard relationship between the database and the cache. The core rule of EVCache is strict. Synchronous user read requests must never hit the database. They are only allowed to read pre-computed payloads directly from the cache. To make this work, the architecture moves computation out of band. background worker threads continuously calculate personalized data, fetching from the database and pushing results into the cache, completely independent of the web request lifecycle. These background workers require their own concurrency protection. The system utilizes lock-free bounded channels. During an unexpected traffic surge, these channels cap memory allocation by safely dropping the oldest queued work, maintaining strict memory equilibrium. Shifting complex database processing out of the reactive synchronous user path and into a proactive asynchronous background path mathematically immunizes the system against thundering herds. A final architectural threat surfaces when data is split across polyglot databases, for example, storing strict billing data in an ACID relational SQL database, while high-velocity telemetry lives in a NumSQL document store. This diagram highlights the distributed application join anti-pattern. A service fetches IDs from SQL, then loops through NoSQL to fetch telemetry. The network math is brutal. Fetching 30 users requires 91 network hops, tying up threads for nearly 1,500 milliseconds. We can eliminate this loop using event-driven denormalization. Instead of joining data on the fly, we utilize integration events, like a subscription upgrade, to trigger background updates. When an event fires, a handler denormalizes updated billing data directly into the NoSQL document. The optimization is massive. Fetching a user profile is now a single parallel point read, dropping query time to just 8 milliseconds. This architecture actively chooses data duplication and minor eventual consistency. It is a deliberate trade-off in exchange for maximum read path velocity. Pre-joining data via events eliminates application-level looping. It converts a dangerous scaling bottleneck into a guaranteed constant time operation. Theory requires practical proof. We can validate the resilience of this architecture using automated chaos engineering. This diagram maps our chaos test. In Phase 2, we issue a pause command to the entitlements API. In Phase 3, we blast the upstream API with concurrent requests. The circuit breaker detects the failure, trips open, and returns a 503 service unavailable header. This enables client-side graceful degradation. The front-end application intercepts the 503 error and the retry after header. Instead of crashing, the UI instantly swaps to a pre-cached offline catalog. An amber countdown timer indicates the retry window to the user. Finally, in Phase 4, the test unpauses the back-end container. The half-open probe succeeds, and full normal traffic flow is restored, without requiring a system restart. Cloud-native resilience relies on building isolation boundaries so strict that a component can fail entirely without degrading the user experience.